Hi, in exercise WT-3 we are to check several alternatives for the drivetrain architecture. So we will be looking at the gearboxes with a different number of stages and different gear ratios, and the point in this exercise is to check how the gear ratio and inertia of the drivetrain influences the acceleration of the propeller of the tidal turbine when the power is lost in the system and there is no more torque provided by the generator to brake the propeller. So now only the water flow will be acting on the propeller without any counteracting from the generator side, and the propeller will accelerate. You know, the water flow is extremely powerful and it is pushing on the blades, making the propeller accelerate quite fast. So we will check how fast in this exercise. Solving the problems in this exercise will be relying on the well-known torque equation. So in our context, TL, low torque, will be the propeller torque, the torque produced by the water flow acting on the blades of the propeller, while TE, the motor torque in this exercise, in our case will be the torque produced by the drivetrain, which will be counteracting the torque from the water flow. So we will simplify the torque equation and use differences instead of the derivatives. So you see the speed difference and time difference in this equation is what we substitute for the derivative, which is acceleration. And from this equation, from this simplified equation, we get the expression that we need. This omega 2 is the speed right before the brake closes. So this is our point of interest, so how much the propeller would accelerate. And of course the key question here is how to find inertia for the torque equation. So inertia of the drivetrain will be made by the inertia of the propeller itself and inertia of the gearbox and the motor. But since the motor inertia is multiplied by gear ratio squared, it will be the dominating component. So we can skip the gearbox inertia for our simplified study. So for each design case, the key question is how to find motor inertia. So we enter, of course, the tidal turbine main parameters, speed, torque and overspeed, and then we need to choose the right voltage level to make the drivetrain operate in DriveConstructor. So we go for quadrant solution because it is a generating solution, the tidal turbine. And then still it cannot find any variant just before we increase the gear ratio to 6, and then the variant is there. So we choose electric machine and scroll to the right, and almost in the end we find the moment of inertia. This is what we were after. This is what we can put in our torque equation. So we recommend you make a table, something like the one you see on the screen, and there you put the gear ratio and the speed of the electric machine after the gear and the respective torque and other parameters that you see on the screen. If we look into the cells, like for example cell C8, we can see how the calculations are done here. So inertia seen by the propeller is calculated as the sum of the propeller inertia, which is 10, and the product of the gear ratio squared and generator rotor inertia. So this is generator rotor inertia is what we calculate every time in DriveConstructor for all the gear ratios and all the gear types. In cell C10 we can see how acceleration is calculated. If you go back and look at the torque equation, you will find how to calculate acceleration. In this case it is the ratio of the torque seen by the propeller and the inertia seen by the propeller. In cell C11 you can see how the speed is calculated, and this is according to the equation, the simplified torque equation that you saw earlier in this video. And in cell C12 we see again the same expression for speed, but here the time is not 0.1 but 0.2 seconds. This is the second case when the brake is applied longer after the grid loss. So this is how you solve this exercise. Thank you for watching.